Hi, everyone. It's a pleasure to be here. Today, I'll talk about some of the work I did at Michigan with my wonderful advisors, Harsha and Ravi, and my lab mate, Jingyuan. So I'm sure some of you are thinking that why are we talking about crawling in 2024? After all, crawlers have existed since the inception of the web itself, which has been more than 30 years at this point. And given the large amount of work in this space, isn't this a solved problem already? Well, turns out it is not. And before I dive into that, let me motivate the need for scalable web crawling. There are a large number of services today that rely on this ability. The most common one is search engines like Google. They rely on crawlers to be able to index all the pages on the web so you can discover information easily. More recently, there has been an explosion in the use of GenAI tools. Now, these tools also rely on crawlers to be able to extract information from the web so they can train and build ML models efficiently. There are a large number of web archives, such as Internet Archives, that take multiple snapshots of pages using these crawlers so that users can visit them at some point in the future in case they cease to exist on the live web. Now, traditionally, all these crawlers have operated in a static manner. To see how that works, let me give you an example. In order to crawl any given page, the first thing these crawlers would do is that they would download the HTML for that page. Thereafter, they'll start statically parsing the source code, looking for URLs. They might come across URLs to external pages, which they will queue so that they can crawl them later. And they might come across URLs to embedded resources, such as images, that will be downloaded as a part of downloading this page. If you would notice, there is certain JavaScript code on this page as well. But these static crawlers will not execute it because they are fundamentally incapable of doing so. So what's the issue with this? Well, it turns out that these static crawlers result in poor fidelity. So in front of you are two screenshots of the same website, abcnews.com. In one of them, I loaded it using Chrome. And in the other one, I disabled the JS execution engine inside Chrome. As you can see in the latter case, a number of images are missing. And this is because they are only fetched when the JavaScript on the page is executed. Now, this is not a new problem. Crawling practitioners already know this. And so they have started using browser-based crawlers in their architecture. And what that looks like is that they integrate the headless browser, which not only comes equipped with the latest JavaScript execution engine, but it also provides support for all the latest and evolving HTML, CSS APIs. So great, you have fixed the fidelity issues we described earlier. Now, naturally, the next question is, what about the performance of these crawlers? To estimate that, we conducted an experiment where we measured the max throughput, which was measured in pages per second, on a given server with 16 cores and 1 gig network. As you can see from this result, the dynamic crawler performs significantly worse, specifically 88% in our case, compared to the static crawler. Now, in order to understand why this is happening, we also measured the corresponding resource utilization for the CPU and the network on the server. So when we did this for the static crawler, we observed that at max throughput, network was the resource that was fully saturated, indicating that for the static crawler, it's network bound essentially. On the other hand, when we repeated this experiment for the dynamic crawler, we observed something very different. As you can see in this particular case, CPU was a resource that got saturated first, indicating that dynamic crawlers are CPU bound. More interestingly, the resource utilization between CPU and network was so high that you would need about 500 cores to even fully balance a 1 gig network. So as you can see from this, the crawling workload has migrated from network bound to CPU bound, and you end up with the following unfortunate trade-off. Either you suffer from the poor performance of dynamic crawlers or the incompleteness of static crawlers. Well, in order to resolve this paradigm, we want to turn the crawlers and we want to make them sprint. And so this is where our system comes in, Sprinter, which seeks to enable high-speed crawling without degrading fidelity. And it does so by strategically combining both static and dynamic crawling techniques. The design for Sprinter is rooted in our two key observations. First, large-scale crawlers will typically crawl a large number of pages for every site that they download. And second, while crawling these different pages on the same site, they often perform similar computations. So if you look at these different articles hosted on bbc.com, even if they might look slightly different, these crawlers are performing a lot of repetitive computations while downloading them. And based on this, we proposed our first key observation, idea essentially, which is to be able to reuse computation across pages of the same site. And by computation here, I'm referring to JavaScript execution. To see how that works in practice, let's look at an example of two pages, page 1 and page 2, that we need to crawl. And there is certain JavaScript code on both of these pages. Different color here represents different section of the JavaScript code. The first thing that we need to do is to rewrite this JS so it's capable of tracking all the state that it accesses. After which, we can crawl this page using a browser. And as a result, you will create this computation cache. This cache essentially is an input-output pair. Input is all the state that it reads. So it can read values from the HTML tree, from JavaScript heap, etc. And a write or outputs is all the values that it writes. So it can write, again, values to the tree or the heap, or it can fetch URLs. In the rest of this talk, I'll refer to this cache as the JavaScript signature. Now, you can repeat this process for the second page. And apart from writing cache, it can also read some of the cache because it encounters certain JavaScript that was already executed as a part of the previous page. So as a result, you have minimized the JS overhead. Good. But if you'll notice, we are still crawling both the pages using a browser. And I've already established that browsers are compute intensive. Well, here is our second idea, where we try to enable crawling a page even without using a browser. To see how that works, let's now add a new page, page 3. If you would notice, the JS on this page is already executed as a part of the previous two pages that were crawled. So you're not getting a whole lot of benefit by crawling this page using a browser. Instead, all we need is a lightweight crawler that is capable of reading that cache and accurately predicting the outcomes of the JS execution on that page. In order to realize this vision, there are two challenges that we need to solve. The first challenge is with respect to the caching granularity. The finer you cache at, there's higher reusability, but also is the higher cache management overhead. The second challenge is with respect to minimizing the use of the browser. So I've established that browsers are compute intensive, and so we need to maximize the number of pages that you will crawl without using one. Let's start with the first challenge. So one level in which you can perform this caching at is function level caching. That means that you have a cache entry for every JS function invoked. Now, the good thing is that since you are caching at a finer granularity, you can enjoy higher reusability and a higher cache hit rate. But given the large number of functions on modern pages, it also results in very high cache management overhead. So clearly not the best approach. On the other hand, if we do something like file-level caching, then we have a single cache entry for every JS file executed. So great, we have significantly minimized our cache management overhead. But now the reusability has also gone down. So for example, in our corpus, on the median site, only 40% of JS was reusable across pages. Again, not the best approach. To resolve this, we rely on our observation that crawlers only care about URLs. What that means is that we don't need to perform this tracking for every JS state that is accessed. We can only track that JS state that influences URL fetches. We do this with the help of a program analysis technique called taint tracking. I'll refer you to the paper if you're interested in more details. But the good thing with this approach was that we were able to combine the best of both the earlier levels of caching. So we got high reusability, high cache hit rate, almost twice than what you would have gotten with a purely file-level approach. and we also minimize the cache management overhead. Great. Let's move on to the next challenge. In order to fully appreciate the challenge here, let me give you an example where, let's say we have to crawl n pages. We need to be able to crawl a smaller subset m here, which we will crawl using a browser, and we'll create that computation cache. Note that this will be compute intensive because using a browser. And then you will crawl the remaining pages in a browser-less manner with the help of the cache that you created earlier. And a key property here is that for every page that is crawled without a browser, all JS on that page needs to have a cached entry. So we formulate this problem as an efficient identification of set cover problem. A set cover essentially is the smallest subset of pages where the union of JS in that subset is same as the union of JS on all the pages. But there's a catch-22 here. In order to compute that subset, you need to know what JS exists on all the pages. And in order to get that information, you need to first crawl all the pages. So now to tackle this, let me present you an example where we are crawling two pages, page 1 and page 2. And let's assume that both these pages are loading the same JS file, JS1. We realize that oftentimes when the same JS file is loaded on two separate pages, oftentimes it ends up fetching the same JS file, in this case JS2. We refer to JS1 as a static file and JS2 as a dynamic file. So given our objective of identifying the subset of pages which includes all JS file, instead of that, we identify the subset of pages which includes all static JS files. And the good thing is that when we loaded this static set cover using a browser, we were automatically able to fetch all the resultant JS files. So now let me put together all the pieces and explain the end-to-end design of Sprinter. Sprinter takes as input a set of URLs that it needs to fetch. And in the very first phase, it performs a static crawl, where it only downloads the static JS file, and it computes that set cover. With the help of that set cover, it moves on to phase 2, where it crawls that set cover pages using a browser while executing that modified JS and creating that computation cache. Once it is done with that subset, it moves on to phase 3, where it statically crawls all the remaining pages, essentially without a browser, by leveraging that cache. And clearly on some of these pages, you can incur some kind of a cache miss. And therefore, you end up offloading those pages to phase 4, which is again a browser-based crawl. With that, I'll move on to the evaluation part of my talk. The two key metrics that we evaluate Sprinter on is throughput and fidelity. For the dynamic baseline, we built a custom crawler that was based on some of the most popular open source browser-based crawlers. For a static baseline, we looked at wget2, another open source crawler. And we used a corpus of 50,000 pages, which essentially consisted of 100 random Alexa sites and 500 pages on each of those sites. So let me start with fidelity. In the context of crawling, fidelity can be defined in a lot of different ways. In our work, we did not make any assumptions about the purpose of crawling. And so we define fidelity as the bytes that are fetched by a dynamic crawler, that is a browser-based crawler. As you can see from this result, Sprinter was able to fetch almost all of the bytes that are fetched by a browser. Static, on the other hand, missed on a good number of these bytes because it is fundamentally incapable of executing JS. Moving to throughput, here on the y-axis, I've plotted the throughput as pages per second, and on the x-axis, I've plotted different baselines. As you can see, Sprinter performed almost 5 times better than the dynamic baseline. It was still sufficiently slow, significantly slower than the static baseline because for a certain subset of pages, it still relies on the heavyweight browser. Another interesting metric that we evaluated Sprinter on is how its throughput will change if we change the number of pages per site that we consider. If you recall, so far in our experiments, we looked at 500 pages per site. In this graph, I've plotted Sprinter's throughput on the y-axis and the different number of pages per second that we considered on the x-axis. The red line is the throughput of the dynamic crawler. As you can see, there is a certain case where Sprinter can perform even worse than the dynamic crawler. And this is because the number of pages per site is so low that the overheads that you incurred from browser-based crawling was not sufficiently offsetted by the browser-less crawling. But the good thing is that as you keep increasing the number of pages per site, Sprinter's throughput keeps on getting better. And the key reason behind this is that as you increase pages per site, there are fewer pages in our set cover, which means you're crawling a smaller number of pages using the heavyweight browser. To summarize, today I talked about how web crawling underlies a lot of important systems in today's society. And even though the web has evolved a lot in the past few decades, the crawling infrastructure has not so much. The crawling workload migrated from a network-bound to a CPU-bound workload. I presented Sprinter that performs strategic crawling while enabling safe reuse of computations. And in doing so, it was able to improve the crawling throughput by a factor of 5 without degrading fidelity. With that, I conclude my talk. Thank you.